Hi there, welcome back to our channel. And now we are going to analyze the circuit as shown in the figure. So this circuit consists of an amplifier, let's say A, and it has a positive voltage supply and a negative voltage supply connected across a series combination of capacitance C1 and capacitance C2. We don't know yet if those capacitors are equal in values or not. And then the middle of these capacitors point is connected to the positive pin of the amplifier as shown, and the negative input of the amplifier is connected to the output, or output is connected to the negative input, we can say that. So kind of this is a kind of negative feedback. And we know that this is a difference amplifier, so it is used to amplify the difference between the two signals. Here is your output, and from the positive pin towards the ground you have a capacitance called CP, which is called as a parasitic capacitance. Now what is parasitic capacitance? We have explained. What is parasitics in electrical and electronic circuit and systems? We have explained that in our previous model. So if you're new to this channel, refer to that model, search with the name parasitics in our channel videos, and you'll get the complete comprehensive video on the parasitics in electronics. So we want to analyze this circuit and get the expression for the output. Now let us call this as V1, the voltage at this node that is at the negative pin, and the voltage at this pin that is at the positive, call it as a V2, which is also equal to Vx. And the voltage across the capacitor actually is Vx, and therefore it is equal to V2. And now we have the assumption that the gain, open loop gain of the amplifier, AOL, is pretty high, ideally infinite. That mandates, or that means, the ratio of output divided by this gain is equal to VID. And VID is the difference between the two inputs, V1 minus V2. The difference could be positive or the negative in nature. That's why I have taken the mod or absolute value of it. Now it means if gain tends to infinity, I would say the VID, which is this difference between the two inputs, tends to 0. And that means V1 minus V2 is equal to 0. That means V1 is at the same potential as V2. So taking this concept or applying this concept, which is also called as the concept of virtual short, widely known in op-amp circuits, helps us to simplify the circuit analysis involving operational amplifiers. So we say that, okay, your input voltage is V1 is equal to the voltage at V2. Therefore, this is virtually short to V2. V1 is virtually shorted to V2, or let's say V2 is virtually shorted to V1. And what is the voltage at V1 then? We have to write that. So now let us write V1 is equal to VO, because you see there is a feedback right here. And therefore, we can say that V1 is equal to V2 is equal to Vx is equal to VO. And that's why we say that your output comes here, right? So voltage across the capacitor CP is basically whatever the output comes here. Or we also say that your VO is equal to Vx, and Vx is the input voltage that appears at the positive pin. So we can say that VO is equal to Vx and output divided V O is equal to Vx, and the gain here is 1, right? Because the output of the amplifier is gain times the input, right? Here, and the input is Vx, the gain is 1 here. And this kind of circuit, because it is VO divided by Vx, then it will be 1. Okay, so this kind of circuit is called as voltage follower. And the use of this circuit is acts as a buffer for impedance mismatching or impedance matching, used for impedance matching. The feature of this circuit is that the R in of this circuit is ideally infinite and practically very high, and the R out of this circuit is ideally 0 and practically very low. And that helps us to place this voltage follower between the circuits where impedance matching is required. Okay, having a low output impedance of this voltage follower helps us to supply any amount of current that the load will demand, the load that we will connect to the output of this circuit. And having a very high input impedance of the voltage follower indicates it can be driven by a minimum amount of current, the lowest possible magnitude of the current coming from the input side of the circuit. For example, this is a Vx acting as a voltage source driving your amplifier here. Okay. Now, what is the Vx coming here? What is the value of Vx? That is what we want to decide. So we see that, okay, there is a series combination of these two capacitors. So we say that series connected capacitors, and then at both the ends, we have the positive supply and the negative supply plus minus Vs. So we can actually get the voltage across the capacitor C1 and C2. For example, C2 voltage across C2 will be, let's say VC2 would be, which is basically Vx, right? VC2 is equal to Vx. Okay, will be value of that capacitor multiplied by the total voltage, which is plus Vs minus of minus Vs. So that's the total voltage divided by the value total capacitance C1 plus C2. Now let's say you have for a given values of the capacitor plus Vs is equal to 1 volt. So 1 minus of minus 1. So plus Vs is equal to 1 volt, minus Vs equal to minus 1 volt. So that's why we can put in the values, and then here is your C1 plus C2. So that becomes the voltage Vx, which is equal to C1 2 volts, C1 plus C2. Similarly, voltage across the capacitors will be C1 multiplied by 2, C1 plus C2. So choose the values of C1 and C2 and you get the value of Vx. And then output is equal to Vx. That is how the beauty of this circuit. You might have some comments about the explanation of this concept here. So place your comments in the videos, in the description and in the comment section. If you like the video, hit the like button, subscribe to our channel, share it for wider use of others, and stay tuned for more engaging contents on analog circuits and systems. Till then, wish you happy learning.